First, thanks to the organizers, especially Mirko, for inviting and giving me the opportunity to listen to wonderful talks over the last couple of days. It was an absolute pleasure. I'm Arindam, and I come from Bangalore, somewhere here. This is my institution. If you have not been there, please come. My group and my collaborators, most of the theoretical work was done by Jill Jung from University of Seoul, and we get boron nitride from the same place that you do. We have heard very different types of, large varieties of talk, wonderful talks, but we haven't heard of noise. And the reason behind that is that, a statement is written here. We usually try to eliminate noise rather than, explore what noise gives. And if I do the right job today, what I would like to establish or convince you about is noise is not really something that you are being unfair to noise. And it actually can, if you can interpret it properly, it can give a lot more information than a standard transport or optical measurements can. Okay, what kind of noise we will be talking about today? So if you get an electronic device, it's usually two types of noise, or three types of noise that you get. This usually is a data sheet that most electronic devices come with. There is, at high frequencies, a noise which is independent of frequency, and there is a very broad range of low-frequency noise that comes in this region, and this is usually called 1/f noise. What we will be talking about today is 1/f noise and what kind of information we can get from the physics of twisted bilayers from using 1/f noise. Just because noise is not a standard probe, let me quickly go through a very quick tutorial. Usually the noise looks, in any electrical measurement that you do, it looks like this over a very long time scales in the order of a second or so. And this time domain function is usually, the challenge comes in measuring it because those fluctuations are extremely small. They're typically depends on the system, can be about 0.1 part per million to about 100 or 1,000 parts per million. So that's where the challenge comes, because if you are measuring a resistance of about, say, a kilo ohm or so, you have to measure a milliohm or a 100 microohm resistance fluctuations, which is sitting on top of that. That's the challenge. And that essentially is overcome by applying amplifications and shielding and so on and so forth. Okay, so if I do a Fourier transform or take a power spectral density of these fluctuations, it usually comes like this. This is why it's called 1/f. But usually, particularly if you're not very lucky and the noise level is very small, then they are normally buried under the Johnson noise, under the amplifier noise, and also the shot noise, which are usually white in nature. And there are ways of phase-sensitive detection in which you can get rid of those white noise from your measurements, and you can concentrate on the 1/f part. Usually for the field effect devices, you have a channel, and the oxide layer or the insulating dielectric layer is a source of noise, major source of noise. Usually they go back and forth, creating a two-state system, right? But this is not one two-state system, but there are many of them. So what happens is you essentially add up the contributions from very large fluctuators of switchers or two-state systems, and if you sum up all the Lorentzians, each two-state system, the power spectral density is a Lorentzian, but then if you sum up all the Lorentzians, you will see that you will get 1/f type of a power spectrum. This is the key source of 1/f noise in most solid-state devices that we see around us. What I'm going to do today, I'm going to do a very quick primer on the graphene-based devices, then twisted bilayer. I'm not going to go to detail at all, but just for what is essential for our work, I'll show you what's the origin of low-frequency noise in twisted bilayer systems. I'll show you unique noise spectrum in this kind of system, and then finally, I'll tell you how noise can actually help you in getting new phases or discovering new phases in 2D, such strongly correlated to the systems. In graphene, if I put it on a silicon oxide, you can do boron nitride as well, but the physics remains same. Usually, noise comes from an exchange of charge between the channel and the traps very close to the graphene layer. What happens is you change stochastically the number of electrons in the channel, but when you lose a charge, it goes and gets trapped in a trap which is very close to the graphene channel, and hence applies a Coulomb potential back on the graphene channel. So both number fluctuations and mobility fluctuations come simultaneously, and all these are usually combined into a model which has been a very old model called a Mach-Horter's model, in which the noise power spectral density is directly proportional to the transconductance square divided by the current, as well as the number of traps that you have in the underlying layer of dielectric. Usually this is about 10 to the 17th electron per electron volt per cubic centimeter in silicon oxide, slightly lower in the boron nitrides that we have. Okay. So how will it look like for graphene? So if you have graphene, which looks something like resistance versus gate voltage, if I get a noise measurement, you can see it should look something like if a derivative of the current resistance versus gate voltage, and it should dip somewhere at the Dirac point. And this is one of the key observations in most graphene devices. At the Dirac point, there is a minimum of noise, and overall, the shape is called an M shape in the noise community. Okay, then traps, I'll just give you an example. You can see a graphene device which is sitting on boron nitride and on silicon oxide simultaneously, something like this. And the noise on the boron nitride part is about a factor of 100 lower than the noise which is sitting on the silicon oxide, clearly telling you that the number of traps is one of the key sources of noise in graphene devices. In addition to that, the contacts are also very important. For example, if you do a 2-probe measurement on this, you see the noise is again about 10 to 100 times larger than the 4-probe measurement of noise in most graphene or 2D devices. This is true whether you're measuring graphene or whether you're measuring TMDCs and so on and so forth. Okay. Over the years, we found there are a large number of possible sources of noise that needs to be reduced. For example, the substrate traps, absorbates, the band structure itself, the polycrystallinity, whether you have grain boundaries or not, or the metal to 2D channel contacts. These are all potential sources of noise in graphene devices. We have recently come up with probably one of the best or the quietest graphene sample made ever. In that, this is something that you would like to take a look at. This is, you see, this red one is obtained when the graphene was encapsulated by the market boron nitride, whereas this one is obtained when the graphene was encapsulated by the boron nitride we got from NIMS. So this is another beneficial effect of boron nitride that often goes unappreciated. It not only gives you fantastic mobility and high-quality channel, but it also reduces noise substantially because of the high quality of the boron nitride. Okay, coming to the twisted bilayers. The twisted bilayers have got prepared in the same way, tear and stack method. I'll not go into that. I'm guessing most of the people know here. We just use the boron nitride to cut the graphene and then twist it in whatever ways. And I'm going to give you 2 different classes of samples. One is a boron nitride, which is a twisted bilayer, which is encapsulated with a boron nitride, and another twisted bilayer, which is partnered with a layer of transition metal dichalcogenide, the WSE2, which is an insulating layer. But the goal of that experiment was to create a proximity-induced spin-orbit interaction on the twisted bilayer. Both these samples, very importantly, there was no superconductivity, although they were fairly close to the magic angle. We couldn't find any superconductivity or any form of strong features in the correlated insulating phase, which we believe is because of the strong inhomogeneity in the twist angle. And this is an important point to note, because we are measuring resistance versus gate voltage. I'm going to show that resistance versus gate voltage does not give you the full picture. The moment I measure noise, the correlated feature starts coming out, but that is at the end. What happens when you measure this noise at high temperature? It looks very benign, very featureless. You do power spectrum, you get 1/f noise, and you get this beautiful M-type feature for both type of samples at high temperature. The minimum at the Dirac point is obvious. Now, in order to compare the noise from different systems, there is a standard method, and that method is called using the parameter called a Ghosh parameter, which is essentially normalizing the noise magnitude by the number of carriers you have and the DC resistance square. That's a standard method. You can use the Ghosh parameter to see or compare noise level in a very broad class of systems. Now, what happens, and this is the first piece of interesting news, is that when we go closer to the Dirac point, there are three samples of three classes of angles. This is 2 degrees, 1.4 degrees, and 1.1 degrees. And when you see the noise, it comes down quite substantially when you are close to the magic angle. These are the first experiments of low-frequency noise in twisted bilayer samples. The noise is significantly lower, and I'm going to show you by how much, when you are sitting very, very close to the magic angle, which is good news if you want to make a device, although there are other constraints, of course. So if I take a look at overall magnitude of noise in a very wide class of graphene-based samples, we have been working on this for a while. When we started in 2009 with a single-layer graphene, the noise level, the Ghosh parameter was here. We optimized various parameters over the years, and it came down to about 10 to the power 5, 10 to the 6-ish in pure single-layer, wonderful boron nitride encapsulations. But now, with the twisted bilayer graphene, we have now gone down by another factor of 5 or so. Clearly, twisted bilayer graphene at that magic angle is one of the quietest graphene-based samples that we have today. The reason behind it is probably because of extremely flat bands at the 1.1 degrees, which means it's a very high density of states, and very high density of states means very high screening. Probably twisted bilayer graphene is better at screening the disorder potential that's essentially floating around in the dielectric layer around it. Okay, so what happens at 5 Kelvin? I have now gone down to lower temperatures. This is at 5 Kelvin. There's something really interesting and weird. We didn't expect it. When you are near the Moire gap, we started seeing this interesting random telegraphic signal. Again, one of the unexpected noise. Whereas if you are within the Moire band, far away from the Moire gap, then the noise is nice and featureless and 1 over f type. As a result, if I plot this noise as a function of the filling factor of the Moire band, you see that inside the Moire band, it is 1 over f, and the noise is low. But at the gap, it increases substantially, primarily because of the fact that there are these random telegraphic signals starts coming in. We ask the question, why? And in some sense, we probably have an understanding. I can't go to the detail, but this is like a generation recombination noise that often people see in standard semiconductors. In a standard semiconductor, you have conduction band and valence band, and there are these impurity bands. And when the impurity band's energy from the offset kind of resonates with the temperature, then you will see that this is a photon frequency, and this is E by KT comes to about 10 to the 12. Then in that case, you get a switching of charge between the impurity band and the conduction band at the experimental timescales of a few seconds. And this is something that is probably happening in this case as well, except for the fact that we don't have an impurity band inside the twisted bilayer, but the impurity band is probably sitting in the boron nitride. If you take a look at the energy defect structure in the boron nitride, you have these carbon vacants, essentially carbon impurities on nitrogen sites, which form a band of defects about 12 millielectron volts above the conduction band or the Moire gap in the twisted bilayer. And that can lead to a noise of generation recombination noise because of the switching of charge from here to there at a rate of about 1 hertz to 10 hertz, and that's exactly what we see in the experiments. Okay, my final question now that, okay, can I now use noise in looking at correlated states in the twisted bilayers? All right? So we all know where the correlated states can come from. If you have a larger angle, a linear dispersion, the two layers are essentially uncorrelated to each other. But if you're going at 1.2, 1.1-ish angle, there is a chance of very flat bands, large density of states, trunculum interaction, and new states. Typically, you have one of the features of strong correlation is in this oscillations of resistance as a function of carrier density, where the peaks in resistance is observed at band fillings of commensurate type. This is filling factors of 1, 2, 3, and 4. And 4, of course, is the Moire gap. Okay. Now, the understanding of this is so far seems to be a series or a cascade of left-shift transition. When you start filling a band of 4 flavors of coming from the layers and the isospin, then in that case, once you start filling all of them together. But then at a particular point, when it's exactly fulfilled, then one of the bands come down, essentially leaving 3 other bands empty. So this is something like a Dirac point. You have got one band completely filled below the other bands which are completely empty. And then you start filling the other bands successively. So this continues, and this is why there are peaks in resistances at 1, 2, and 3. Of course, there are other reasons. Now, if you had a sharp eye, then when I showed you this data, you would have seen that there are tiny dips in the noise at filling factors of 1, 3, and so on. This was not particularly well done or understood. So what we did, we repeated this, and it looks like that if I now do noise measurements in this twisted bilayer, where the resistance does not show any feature at all, this is at 5 Kelvin. Okay? And this also has a huge angle in homogeneity. So there was absolutely no feature whatsoever between the Dirac point and the Moire peak. But if you see noise measurements, you can start seeing small minima at 3, 2, as well as 1, which we interpret is as something which is coming from the cascades of Dirac points continuously going on top of one after the other. What happens if we now start doing this with a TMDC layer? So what we did recently is that when we have a TMDC layer next to the twisted bilayer, the proximity-induced spin-orbit coupling probably has led to new states around half-integer filling of the Moire band. We're almost done, right? 1 minute. Yeah. So we see this 3.5 phases that comes up because of the additional presence of the TMDC layer. But we did, our theoretician colleague Jeljung essentially said that this could be because of apparent lattice doubling effect, because of we are forming presence of the TMDC layer leads to a spin charge density wave, which essentially doubles the lattice, and now it contains 16 bands instead of 8. Very good. So when we did a Hall effect as well as thermoelectric measurements, we only found new states at half and 3.5, although a lattice doubling would have given the effects at half, 1.5, 2.5, and 3.5 as well. We never found them. So we ended up doing noise measurements here, and now you see the noise measurements in these systems are amazingly rich, even though electrical resistance measurement shows virtually nothing. You can see now we have this very strong dips or very interesting emergent Dirac points at 3.5, 2.5, 1.5, in addition to the integer filling factors. So that's where I am. I'm done. I'm out of time. The summary of this work is that noise could be a more sensitive probe to the correlated phenomena. Hopefully, I've been able to convince you on that. In addition to that, noise in twisted bilayer graphene, as far as its magnitude is concerned, is one of the lowest noise magnitude in known graphene-based devices. And the third, this half-integer filling seems to be quite an interesting direction, and we would like to understand more on that. Thank you very much for your attention.
Thank you for the nice talk. Questions? I see, yeah.
Yeah, thanks a lot for the talk. I was curious, one of the time traces you showed us on telegraph noise in the twisted bilayer,
right.
I think it was at filling factor 4,
yeah.
Was remarkably regular. In fact, it doesn't look like noise at all.
No, but we do have, okay. I'm sorry, I think because we probably have shown you a snapshot of the full time series, but it is reasonably, I think I'll just quickly, it's the very previous one, so. Yeah, so, so this is the, yeah. Okay, so yeah, well, I mean, maybe that one is looking, yeah, I agree with you, this is looking regular. Whereas these are the ones which are relatively, sorry, I mean, I'm sure we have taken a time series which seems regular here, but it's not always regular.
Okay, so you will have to inspect the frequency spectrum later.
So most of these are Lorentzian power spectrum.
Okay, please.
Thank you, Professor Ghosh, for the very insightful talk. My question is, all the data and measurements that you have shown here basically talks about autocorrelation measurement. I'm wondering if you think there would be a merit of measuring cross-correlation with having two drains in your system, simultaneously measuring currents in them.
Well, I mean, yeah, of course, why not? I mean, noise measurements is essentially autocorrelation of resistance. You take resistance at time t and then time t plus tau. You can always do cross-correlation. It will not be noise in the present form. It will be something else. But yeah, why not? I mean, you can do that. But I don't know of any new physical insight you will get from those measurements. Yeah.
Okay, thank you. Next question. Yeah, please.
From technology point of view, I'm looking for low noise electrodes.
Yeah.
Your quietest, whatever, magic angle graphene, how does the noise compare to the just metal conductor?
Right, so actually that's one of the advantages. The metals are far noisier than graphene if you make them properly. The Ghosh parameter for a metal is in the order of 10 power of minus 3. That's the noise value, or the dimensionless noise parameter. We have been able to go down to 10 power of minus 6 with graphene-based devices. The difficulty, the overall noise magnitude comes to a problem because the graphene is much smaller in volume. So the denominator becomes smaller, so overall noise might increase. But the intrinsic noise magnitude in graphene is much smaller than standard metal.
Thank you, Professor Ghosh, for your talk. I just want your comment on the effect of strain on the 1F noise on this TMD, twisted materials.
Usually the strain does not involve noise in particular unless it opens a gap. So if you open a gap, then you start reducing the screening ability of the electrons because the density of states is going down. That can increase noise. But it's not necessarily to be the truth in every system. It will, in some cases, strain can dope, for example, and then the noise might come down. So it needs to be taken in a case-by-case basis. There's no universal answer.